This marks the beginning of our third unit where we're going to start looking at trigonometric identities. An identity is defined as a statement of equality, so an equation, if you will, that is always true regardless of the value of the unknown or the variable. We've seen some trig identities already. We're going to look at quite a few in this unit throughout the next few videos. And just keep in mind the value of a trig identity is to allow us to make substitutions to make problems easier to work with. So we'll see the use of trig identities at the end of this unit when we start looking at trig equations. You'll also use trig identities a lot in your calculus sequence. Our fundamental identities include our reciprocal identities, Pythagorean identities, and even odd identities. We've already seen those reciprocal identities that are showing the relationship between functions like sine and cosecant, cosine and secant, tangent and cotangent. I missed this other one. Our quotient identities, tangent is sine over cosine, cotangent is cosine over sine. And our Pythagorean identities. Obviously, we've seen the use of sine squared plus cosine squared equals 1 many times already, but we have these two other Pythagorean identities that can be very useful for us when solving trig equations. Some new identities we're going to look at, though, are our even odd identities. So when we talk about even and odd, that characteristic of a function has to do with its symmetry. So we want to recall that an even function is one that's symmetric about the y-axis. And we verified back in an algebra course that an even function satisfies this statement that your function f of x is equal to f of negative x. In other words, for any input x, if you were to plug in the opposite of x, then you would get that same function value. An odd function is symmetric about the origin. And it's true that for an odd function, negative f of x is equal to f of negative x. So thinking about if we were to plug in any value of x and find its y value, if we took the opposite of that, so the negative of that output, that would be equal to that function if we were to plug in the opposite of that x value. So let's think about our three main trig functions, sine, cosine, and tangent. When we think about sine of x, and I'm going to quickly sketch this graph, sine of x, thinking about starting at the origin at that midline, then going up to the maximum, back to the midline, down to the minimum, back to the midline. And this pattern continues. So if we were to go towards the left from the origin, from that midline, we would go down to the minimum and then back to the midline. And we can sketch that nice curve that we know would continue to repeat itself over and over again. When we see these points reflected about that origin, that tells us that sine of x is an odd function. And so sine of negative theta is equal to negative sine of theta. Similarly, if we were to look at cosine of theta, when we're starting at x equals 0, starts at its peak, goes to the midline, down to the minimum, back to the midline, back to the peak, and we can continue that pattern to the left of the y-axis. If we start on the y-axis at that peak, then we come back to the midline, and even just looking at that one point, starting to connect these points we have, we can see that this is reflected over the y-axis, which tells me that this is an even function. Since cosine is an even function, cosine of negative theta is equal to cosine of theta. And then our function for tangent, sketching that parent function. Tangent we know has vertical asymptotes at negative pi over 2 and pi over 2. And then we have that cubic-like function going through the origin. And if we were to look at those points a little more closely, which you could do from our Unit 2 videos, we would see those 2 points on either side of the origin that are reflected about the origin, telling us that this is an odd function. And so tangent of negative theta is equal to negative tangent of theta. Knowing these even odd properties, again, allows us to evaluate these three trig functions for different values of theta, and then we can consider the other sign of theta. So let's see how this is used in practice. Find sine of theta given the following information. We know that cotangent theta is negative 1/5 and theta is in the fourth quadrant. If cotangent theta is equal to negative 1/5, this tells me that tangent of theta, which is the reciprocal of cotangent, is equal to negative 5/1 or just negative 5. And I'm going to keep this as a fraction over 1 because we want to be thinking about tangent and how it's going to relate to the triangle we're going to build. So having those both of those values is going to be helpful. If you recall, tangent's going to be that y value over the x value. And since we know that theta is in quadrant 4, that means that the x has got to be the positive value and the y has got to be the negative value. So if we graph our angle that has a y value of negative 5 and an x value of 1, we can set up our right triangle. 1, this is negative 5. We can use the Pythagorean theorem to help us find the value of the hypotenuse, which is what we're going to need if we want to find sine of this angle theta. Squaring both legs and then adding those, r squared, or you can write hypotenuse squared. It doesn't make any difference. You can do c squared if you're used to that version of the Pythagorean theorem. But really what we are looking for is the length of that hypotenuse. It's going to be 1 plus 25 r, excuse me. R squared is equal to 26. And then we're going to take the square root of both sides. And r is always going to be that positive value since it's representing the length of that hypotenuse. So r is equal to the square root of 26. And now that we have our triangle complete, we can evaluate sine of theta. Theta is going to be opposite over hypotenuse, which is going to be negative 5 over the square root of 26. Since we always want to make sure that our denominator is rationalized, we're going to multiply by the square root of 26 over the square root of 26. Negative 5 times the square root of 26 over 26. And that's not going to simplify any further. So sine of theta is equal to negative 5 times the square root of 26 over 26. In this example, we were using those quotient identities. I'm sorry, actually, we were using the reciprocal identities, the reciprocal of cotangent being tangent. Find sine of theta. Again, those are the directions, given that cosine of negative theta is equal to the square root of 3 over 6, and cotangent of theta is less than 0. Because cosine is an even function, cosine of negative theta is the same as cosine of theta. So this first fact tells me that cosine of theta is also equal to the square root of 3/6. Since cotangent is negative, that means tangent is negative. So tangent of theta is negative, and that happens in quadrants 2 and 3. I'm sorry, Q2 and Q4. Cosine being positive happens in quadrants 1 and quadrant 4. So if both of these pieces of information need to be satisfied, then that tells me that our angle theta has to be in quadrant 4. Setting up our angle in quadrant 4, cosine was given as the square root of 3/6, which is our adjacent side to theta. So the square root of 3 and 6 is the hypotenuse. Now we need to find the y value using, again, the Pythagorean theorem. 6 squared is equal to the square root of 3 squared plus y squared. 36 is equal to 3 plus y squared. Y squared is equal to 33. And now we need to take the square root of both sides to get y by itself. When we take the square root of both sides, we need to be thinking about whether the sign is going to be positive or negative, because if we look at this abstractly, both the positive square root of 33 and the negative square root of 3, when we square them, gives us 33. So if we were solving this without any physical application, we would have two values of y. However, because y is now representing a position on this graph, and we are in the fourth quadrant, y is going to be negative. So this is negative square root of 33. Now that we've completed the triangle, we can evaluate sine of theta. Sine of theta is opposite over hypotenuse, which is going to be negative square root of 33, or that y value, over r, or the hypotenuse 6. Determine whether the function f of x equals sine x over x is odd, even, or neither. So to determine if this function is odd, even, or neither, we're going to use those notes that we took just a few moments ago on even and odd functions. Remember that an even function satisfies f of x is equal to f of negative x, and an odd function satisfies negative f of x equals f of negative x. So we're going to first test for even, because we already have f of x, so all I need to do is compare that to f of negative x. So we're going to find f of negative x first, and all we're going to do is simply substitute a negative value or negative x everywhere we see x in that function. So this is sine of negative x divided by negative x. When you're writing this type of workout, it's really important that we pay attention to notation. I see a lot of students just write f of x equals sine of negative x over negative x, but we really do want to be mindful of changing out that argument or the value of our variable so that the work that follows is represented by what that function is named. Using our even odd properties, we know that sine of negative x is equal to negative sine of x over negative x. And now those two -1 coefficients simplify to +1. So this is equal to sine of x over x, which is equal to our original function f of x. So since f of x is the same as f of negative x, which we just shown, f of x is even. And that tells me that this function would be symmetric about the y-axis. Now we could move further to test if this function is odd, but if a function is even, then it cannot also be odd. And I want to emphasize here that I am describing these equations as functions, meaning they pass that vertical line test. If we're given an equation written in function notation, such as what's given here, f of x equals sine x over x, they are telling us that this is a function. We don't need to go in and verify it. We can trust that any equation that is not a function is not going to be presented in function notation. So to re-summarize what I was just saying, if we have a function, we know that the equation is a function, so it satisfies that every input has exactly one output. If we have a function and we know that that function is even, then it cannot also be odd, because if it was also odd, then it would no longer satisfy the requirement of being a function. So we don't need to test any further because we have verified that f of x is even, so we know that it's not odd. Simplify the following to a single trig function or number with no denominator. So this example, we are starting to touch on verifying trig identities. This is something that we're going to look at more formally in another video. But really what we're trying to do is take a given expression and rewrite it in a more simplified way. So our first example is negative tangent of theta times cosine of theta. I'm going to start with working with that tangent theta expression and rewrite it in terms of sine and cosine. So negative tangent theta is equal to negative sine of theta over cosine of theta. And this is being multiplied by cosine of theta. Now that factor of cosine theta in the numerator and the denominator simplify to 1. So this simplifies to negative sine of theta. So our original expression, negative tangent theta cosine theta, is equivalent to negative sine of theta. Secant theta divided by cosecant of theta. I'm going to take our secant and cosecant functions and rewrite them in terms of sine and cosine. Secant is the reciprocal of cosine, so secant theta is 1 over cosine theta. Divided by cosecant theta is the reciprocal of sine theta, so 1 over sine theta. Now to clear out this complex fraction, we're going to take the numerator, multiply it by the reciprocal of the denominator. So we have 1 over cosine theta times sine theta over 1. Multiplying these fractions across, this is sine of theta over cosine of theta, which now we can see is equivalent to tangent theta. Tangent theta times cotangent of theta. Tangent theta times cotangent of theta is the reciprocal of tangent theta, so 1 over tangent of theta. The factors of tangent and tangent theta cancel out. This simplifies to 1. Now, this particular example could also be looked at in terms of converting tangent and cotangent into function or expressions with sine and cosine. Tangent theta is sine theta over cosine theta. Cotangent theta is cosine theta over sine theta. And now we start seeing these like factors of sine theta cancel out and the like factors of cosine theta cancel out. That language of cancel out, often used in a math class, really what we mean is that it's simplifying to 1 here, but we're very used to that language, that vernacular. Now, here's where I see students make mistakes all the time, is that everything is canceled out, so the answer must be 0. But what we're forgetting are those invisible factors of 1 in front of all of these factors. Those ones, again, divide to 1, and 1 divided by 1 is 1. So the same expression, tangent theta times cotangent of theta, can be simplified either of these two ways. And that's not uncommon either. When we're looking at simplifying these trig expressions, we might find that there are multiple ways of simplifying using different identities. Simplify the following with no denominator. So just a quick observation of the difference in the directions from example 3 to example 4. Example 3, we wanted to simplify to a single trig function or a number with no denominator. Number 4, we're generalizing those directions a little bit more. So we're just simplifying. We want to make sure there's no denominator. So that doesn't mean that we'll end up with just one trig function, but we will make sure that we do not have more than, or we won't have a denominator. Sine squared theta times cosecant squared theta minus 1. We're going to start by distributing sine squared theta. So we have sine squared theta times cosecant squared theta minus sine squared theta. Make sure you distribute that sine squared to both terms inside the parentheses. We're going to use the reciprocal identity for cosecant. Remember, the reciprocal for cosecant is sine. So we've got sine squared theta. Cosecant squared theta is equal to 1 over sine squared theta minus sine squared theta. We can simplify our first term, those factors of sine squared theta, simplify to 1. So we have 1 minus sine squared theta. And this is equivalent to one of our Pythagorean identities just rewritten. So I'm going to write that Pythagorean identity over to the right in green. We know that sine squared theta plus cosine squared theta is equal to 1. If I were to rearrange this by subtracting sine squared from both sides, cosine squared theta is equal to 1 minus sine squared theta, which is what we have. So this simplifies to cosine squared theta. Secant theta minus cosine theta. Secant theta is the reciprocal of cosine, so we're going to rewrite secant theta as 1 over cosine theta minus cosine theta. Now we specified that we didn't want to have any denominators, so we need to clear this denominator, and we're going to do that by getting a common denominator. So our term cosine theta, we're going to multiply by cosine theta over cosine theta. So we have 1 over cosine theta minus cosine squared theta over cosine theta. And now we're going to combine our two fractions since they have the same denominator now. We have 1 minus cosine squared theta over cosine theta. And our numerator, 1 minus cosine squared theta, if we look at that last example where we rewrote that Pythagorean identity, sine squared theta plus cosine squared theta equals 1, we can do this the same or similarly. This expression 1 minus cosine squared theta would have been the result of just moving the cosine squared theta over. So this is equal to sine squared theta over cosine theta. And now to see this a little bit more clearly, we're going to factor sine squared theta. Doesn't factor very interestingly, but it's sine theta times sine theta. And the reason we want to do that is because when we put this over cosine theta, the one factor of cosine theta and the one factor of sine theta in the numerator divided by our factor of cosine theta in the denominator is tangent of theta. So this further simplifies to tangent theta times sine of theta.